All right, everyone, welcome to the next screencast for the first part still of Chapter 5. The upside to this first part taking a while is that once we get to two-dimensional models, a lot of this stuff translates over, so we won't have to recover all of this material for 2 dimensions. It all just translates over into those models. Not everything, but almost everything. So we left off talking about preferred 2 sets. And so a preferred 2 set is for an individual, right? So let's say person B here, and we're comparing what are the set of alternatives person B prefers to, say, 50, right? Let's say 50 is an alternative in the set that is maybe the status quo or something like that. And so we want to know, what would person B vote for against 50? And we said is, because we're assuming single-peaked and symmetric utility, their preferred 2 set of 50 is everything between 40 and right up to 50, and everything between 40 and right up to 30. So the preferred 2 set of person B for the alternative 50 would be everything between 30 and 50 non-inclusive. So that's for an individual. What we want to talk about now is for a group, all right? And what's going to be important here is what alternatives would beat a particular policy. Not just what does one person prefer to a given alternative, but as a group, if they were voting, what alternatives would beat a given alternative. So let's say it's 50 here. What would be the set of alternatives that would beat 50 for this particular set of voters? We have a name for that set. That set is called the win-set. It's a very descriptive name for it. It is the set of alternatives that would win in a vote against another alternative. Usually we call that alternative the status quo. All right. So here is a spatial model. We have 3 voters. They all have single-peaked and symmetric preferences. All right. And so what I'm going to do is I'm going to fill in the preferred 2 sets for each of these voters. So first with Carrie, we know she prefers everything between 40 and 20. Right? If we drew her utility function in, this is her ideal point, therefore it's the peak of her utility function. And so she definitely prefers everything between 40 and 20 because all of those things would give her a higher utility. And of course, because she has single, peaked, and symmetric utility, she also prefers everything between 20 and 0, not including 0. So Carrie's preferred 2 set of the alternative 40 is everything between 0 and 40 non-inclusive. Again, that's why we have the soft parentheses here instead of hard brackets, because 0 is not in the preferred 2 set. It is the boundary. If you have a case, and there will be some in a second, where this number is in the preferred 2 set, then you put a hard bracket. But 0 and 40 are the indifference points for the alternative 40, and so they are not in the preferred 2 set. What about for Adam here? Well, for Adam, we know he definitely prefers everything between 40 and 50. We are getting closer to his ideal point. We are going up his utility mountain into higher utility alternatives, 40, 41, 42, 43, 44, 45. All of those things are better, in Adam's opinion, than 40%. Also, since Adam has single-peaked and symmetric preferences, Adam also prefers everything equidistant on the other side. So 40 and 60 are his indifference points, and they are the boundaries of his preferred 2 set. So the preferred 2 set of Adam for the alternative 40 is everything between 40 and 60, but not including 40 and 60. Again, that's why we have the parentheses or the soft brackets on either side. Now let's take a look at Helen here. What is Helen's preferred 2 set of the alternative 40? Well, we know Helen prefers everything that is between the alternative under consideration and her ideal point. We are getting closer to her ideal point. We are going higher on her utility function. If her utility function had a peak, let's say right here, moving this way, we would be going up her utility function, up utility mountain, as I call it sometimes. So she strictly prefers all of the things between 40 and 80, not including 40. And 80, in fact, she prefers the very most. What about the symmetric side, the flip side for Helen, because she has symmetric single-peaked utility? Well, notice that we normally, what we do is we say between 80 and 40, and then we go the same distance on the other side. But we're talking about percentages here. Usually in this situation, we're talking about the percent of a budget we're going to spend on a particular area, like how much of the budget is going to be spent on catering, or how much of the federal budget is going to be spent on military spending or something like that. So we can't go above 100% here. So Helen's preferred to set is going to be truncated here at 100, all right? So for Helen, the preferred to set is the preferred, let me say it the right way, the preferred to set of Helen for the alternative 40 is everything between 40% and 100%. 40% is not included. That is her indifferent, that is one of the indifference points. The other indifference point would be, let's see, it would be 120, but we can't go there. So we list 100. That's as high as we can go. But notice, 100 is strictly preferred to 40, right? 100 is only 20 away from 80, and 40 is 60 away. So Helen strictly prefers 100. So it is in the preferred to set. That's why we have a hard bracket here, all right? So this is the set of all the preferred to sets for Carrie, Adam, and Helen for this set of voters. What we want to look at next is what are the set of alternatives that would beat the alternative alt, okay? So we're going to assume the alternative we're looking at here is the status quo policy. So this is existing law. So we're going to just relabel it SQ to make it the status quo. This is pretty common, especially when we're looking at pairwise voting situations. To think of one of the alternatives as the existing policy and the other alternative as a proposal. Someone says, hey, I don't like the way we've been doing things. I propose we do this instead, right? This is the way a lot of group decision making works in deliberative bodies like legislatures, in clubs, in committees, and all sorts of things. There's usually an existing way we've been doing things. Even if the way we've been doing things is we've been doing nothing. That would be the status quo. And we put up a proposal and we vote on those things. Sometimes we vote on multiple things at a time, and we'll talk about those situations. But in many situations, we vote pairwise. It's the status quo, what we're doing now versus the proposal. So we're going to call that the status quo. And we're going to look at right now pairwise majority rule. And what we want to know is under pairwise majority rule, pairwise, right, just means two things at a time. Majority rule just means the thing that gets the most votes wins. So we're using pairwise, two things at a time, things that gets the most votes wins rule, all right? What alternatives would beat the status quo, all right? So there are three people. So a majority is two people, right? So we need to find all the alternatives that at least two people or more prefer to the status quo. Well, that's handy because we've already drawn out everyone's preferred to set. So I want to know what is the set of things where at least two preferred to sets overlap. It could be more, but at least two preferred to sets overlap. So what is the set of points where more than two people prefer them? All right, to the status quo. This is what Adam prefers to the status quo. This is what Helen prefers to the status quo. This is what Carrie prefers to the status quo. Notice nobody agrees with Carrie. All right, nobody overlaps with Carrie. The thing she prefers to the status quo, nobody else prefers to the status quo. So what we're going to be looking at is over here. Here, Adam prefers everything between 40 and 60, not including 40 and 60, and Helen prefers everything between 40 and 100. 100 she does prefer, 40 is the boundary. But there's an overlap. For two of the three people, there is a set of things that they both prefer. So this set of things would beat the status quo in pairwise majority rule. So it's this set of alternatives. Everything from 40 to 60, not inclusive, would beat 40. So this is the set of alternatives that will beat the status quo. We call this the majority rule win set. all right? The majority rule win set. The set of things that would win under majority rule is between 40 and 60, but not including 40 and 60, because 40 is an indifference point. We don't, and 60 is an indifference point. We don't know what Adam would vote for if we put 60 up against the status quo of 40. And similarly, if we put 40 up against the status quo of 40, it's kind of weird. We also don't know what Helen would do there. So the win set is everything between 40 and 60, non-inclusive. So from 40.000001, that would beat 40, all the way up to 59.9999999 repeating, that would also beat 40. All the alternatives in between would beat 40. So that is the majority rule win set, all right? So here's a little step-by-step on how to find the majority rule win set. Find each voter's preferred to set of the status quo. Determine the minimum number of votes needed to defeat the status quo. So if it's 3 voters, you need 2. If it's 5 voters, you need 3. If it's 7 voters, you need 4. As I've said before, we will often look at odd numbers of voters because it gets mathematically tricky and complicated, and it doesn't really help us understand anything if we have even numbers of voters. So we're mostly going to be looking at odd numbers of voters. So if there's 11 voters, you need 6 for the majority rule win set. So then you take the number, and here's how you do that. You take the number of voters, divide by 2, and round up to the nearest integer. This threshold is often called K in social choice theory. So the simple majority rule is the K where you have more than a half, all right? So there's also K majority rules for supermajorities, and we'll come back to those later on. But for now, we're going to be looking at simple majority rule, which is the K of 1/2 plus 1 voter, all right? So the next thing we want to do is find all the places where K or more of the voters' preferred to sets overlap. So again, if it's 3 voters, we divide 3 by 2, and we get 1.5. We round up to the nearest integer, which is 2. So K is 2 for that situation, and we want to find the place where K equals 2 or more of the voters' preferred to sets overlap, and that indeed is what we did in the last slide. So what is the relationship between win sets and Condorcet's winners? In fact, there's a very strong relationship between the two. The majority rule win set, I should probably have said to be technically accurate here. So there's a relationship between the majority rule win set and Condorcet winners. A Condorcet winner is an alternative that cannot be beaten under pairwise majority rule. The majority rule win set is the set of all alternatives that will beat a given alternative. So a Condorcet winner has an empty majority rule win set. A Condorcet winner, the win set for a Condorcet winner is empty. There are no alternatives that can beat it. So its win set is the empty set, all right? And the way we write that is the win set of whatever the alternative is equals empty set. And this is, this 0 with a slash is not always just a cool metal looking 0. It means empty set. It means there's nothing there. Not even a 0 is there. There is nothing there, okay? There are no alternatives that beat it, all right? And we're going to use that in the next screencast when we look at something called the median voter theorem, all right? And I will see you then.